Hello all, we're going to start into our third part of the energy unit, the last topic, which is nuclear power or nuclear energy. I'm actually going to use our textbook as a resource for this particular unit, so I'll work directly according to what you see in the textbook. So 19.1 in the textbook talks about electrical energy in Ontario. And we can't really talk about electrical and energy Ontario unless we talk about Ontario power generation. So the first thing I'm going to ask you to do is this short assignment from Ontario Power Generation. It's actually posted in the hub in the Unit 3 Energy Resources for Mr. Senna's notes. Now, when you come to this assignment, they boast a little bit. It says Ontario Power Generation is one of the largest, most diverse clean power producers in North America, and it talks about the 6 forms of electrical energy that OPG uses. Now, there's an app that I like to use. I can't open it right now. I tried it a minute ago and it cut off my recording. So it's called GridWatch, and what it does is it looks in real time at how much energy is being produced in Ontario and where that energy is coming from. In other words, what are the sources for that energy? Like I said, I really like that app because I think it tells us a lot about what we're doing as a province in terms of energy production. So you can see on the left side of the GridWatch menu there, trends. It looks at how it's generated. It looks at our carbon emissions. So all the different things, where the different plants are, total capacity for the province. So it says at that particular point in time. So I made this assignment up here on Sunday night at around 9 o'clock. Actually, it was probably around 10:30, and it said in the previous hour, the amount of energy production by OPG was 16,000 megawatts. Right, that's the power produced. So that's the capacity to use energy. That's not energy, that's power production. And it says that's a pretty average number. And if I look at where the electricity, where did that 16,000 megawatts come from? Well, looks like about nine of those 16 came from nuclear, right? And then about 4 from hydro and about 3 from wind. And that's basically it at that point in time. So they're producing combined about 99% of the electricity that we were using at that moment. These things will change. Again, it was dark, so there was nothing from solar at that point in time. Hydro changes depending on the time of day, and the percent that nuclear contributes, again, will also fluctuate from day to day. Now, if you don't do that, if you go to the OPG website at opg.com. Most of this assignment kind of revolves around the main menu, the menu button, which you're going to see in a minute here, which is at the top of the OPG website. So if hopefully this won't kick me out. Nope. So there's the OPG website. If you go to opg.com, it will bring you to this website. Here's the main menu. Here's the main menu over here. So if you click on the main menu, we're going to be mostly using this Powering Ontario, and we're going to start with overview with our role and our generation. So if I click on overview, okay, it will tell me a lot about OPG in Ontario if it will load. Right now, if you go back to the assignments, it says in Electricity 101, what are the 3 components of Ontario's electricity system? And then it asks you to watch, we're actually in our role. And it says then watch the video. It's about 60 seconds long, and it talks about the 3 components of OPG in terms of Ontario's electricity system. So if I go back just for a minute to here, if I click on our role, which I see over here on the right, there's our role. And scroll down a little bit. There's Electricity 101. Tells us what the 3 parts are, 3 components of Electricity 101. Generating electricity, transmitting the electricity from where it's produced to where it's going to be needed, and then once it gets to towns and cities, there's a distribution system that sends it down streets and into houses and schools and hospitals and buildings and malls and things. Okay, so those are the three parts, and then as you scroll down here, you get to Ontario's electricity system in 60 seconds, and it's just a short little video, and there's some questions. So you'll see as you work through it, you may need to pause this as you're working through it, but you should be able to work your way through that OPG assignment. It's not huge, but I think it's really important for us to recognize those two main components for Ontario's power generation, which are nuclear and hydroelectric power. And we're going to talk about both of those again when we talk about electricity again in chapter 12 and 13, which will be our last two chapters for this course. Okay, so let's go back to Notability. Let's go back to nuclear power. And this note is actually already up in the Unit 3 Energy, Work and Power folder in Mr. Senna's notes. So you'll see Unit 3 notes, Part 3, which is nuclear power. Now, in order to understand what nuclear power is and how it works, just got to look at the name, right? Nuclear tells me that we're talking about the nucleus of an atom. Okay, so the nuclei of atoms, nuclei is plural for nucleus, one nucleus, multiple nuclei. Nuclear energy is energy that's stored inside the nucleus of an atom. Now, in order to understand how that energy is stored within the nucleus of the atom, we need to go back to grade 9 here and look at the structure of an atom, right? Look at the fact that we understand matter using something called the atomic theory. Atomic theory tells us that all matter is made up of atoms, and that the smallest unit for any element, right, there are 92 naturally occurring elements, and that all atoms of the same element share similar characteristic and physical properties. So a carbon atom is a carbon atom is a carbon atom, and a calcium atom is a calcium atom is a calcium atom. All right, so calcium atoms will share chemical and physical properties. Now again, what we've learned about, because we had to learn how to do Bohr diagrams, and we did them until we were seeing dots in our sleep, is if I look at a lithium atom here, I know it's lithium because I see 3 protons in the nucleus. Okay, the protons tell me that it's lithium. I see 3 electrons in the outside of the nucleus. They're in the electron orbits or electron shells. Right? And again, if you've taken 3U chemistry or 4U chemistry already, I'm preaching to the choir here because you understand all of this already. And then I'm seeing those little pink items in the nucleus. Those little pink ones are the neutrons. So I've got protons in the nucleus, I've got the neutrons in the nucleus, and then I've got the electrons, which are outside of the nucleus. And electrons are what we talk about when we talk chemistry. Unless we're talking nuclear chemistry, every other part of chemistry really is about the electrons. Electrons decide what will react, how it will react, what product will form, will there be a product, will there be a reaction or not. Everything comes down really to electrons. This one chapter in the physics textbook, this one chapter in the chemistry textbook, talks about nuclear reactions, different from chemical reactions in a number of different ways. So, to understand the nucleus, right, we're looking specifically at the pluses and the zeros, the protons and neutrons inside the nucleus here. They both have a role to play. Now, one of the things that we learned about in electricity in grade 9 is that opposite charges attract and like charges repel. And one of the things, as we were starting to understand the structure of an atom, was how are these negative charges held inside an atom? We said, well, they've got to be there because they're attracted to the positive nucleus, right? And there is, again, it's not as simple as that, but that's basically the essence. The negative electrons are held in the atom by the positive nucleus. So the question then becomes, why do the positives stay bound together inside the nucleus, right? Why don't they basically explode? Because all these pluses don't like other pluses. If I'm talking about barium atom has 56 protons in its nucleus. That's a lot of pluses to cram into a tiny little space. Again, remember, I'm not sure who you had for grade 9, maybe it was me, but we talk about the fact that this picture here, right here, is really misleading because the nucleus doesn't look like that. The nucleus is a speck. If if this was the size of the atom that we're seeing with its 3 electrons, the nucleus would be invisible. It would be so small in the middle of that picture that you wouldn't be able to see it. Right? So all that positive charge would be crammed up inside that little positive space, the nucleus. The neutrons that are in there, we have since discovered, have an important role in stabilizing that nucleus. They allow that nucleus to stay intact. So we didn't understand neutrons for a long time. We didn't even know they were there for a long time. It's only within the last 100 years that we've discovered neutrons. And we'll talk more about the function of neutrons in atoms in the next section. So when we're talking about an atom, we typically use a standard form. The standard form looks like this, where we have the element symbol, the atomic mass up on top, A, and the atomic number below, Z, or Z. So those 3 pieces tell me a lot about the atom. Now, I don't need to say radon and 86, because I know if it's radon, it has to be 86, and I know that if the element has 86 protons, it's got to be radon. Right? So I can go to my periodic table and say, what is element number 86? It will tell me right away it is radon indeed. So those 2 parts basically are, they're not both necessary because they both tell me the exact same piece of information. The 222 that's up there is the mass, right? It's telling me how heavy that atom is. Now, we've already learned in chemistry that, well, let's not get into chemistry. When we look at the radon atom here, remember, if it's got 86 222, then the 86 tells me that, that there are 86 protons. I know that if there are 86 protons, we learn in grade 9 that the number of protons always equals the number of electrons. So there has to be 86 pluses and 86 minuses. Remember, the mass of every proton is 1 atomic mass unit. And the mass of electrons are basically 0. It's not really 0, it's 0.00005, right? But for the most part, it's close to 0. So we don't count the mass of the electrons. So if the mass is 222 and 86 are protons, then I can calculate the number of neutrons here by taking the atomic mass number, which is the A number, minus the number of protons, which was the 86, number of protons, which was the Z number. So ultimately, I have 222 minus 86, and that equals 142, 136. So I can calculate the number of neutrons in the atom because I know that the protons plus neutrons combined give me the mass of the atom. And a tiny bit more for the electrons, but we typically ignore the electrons. Right, so while in every other thing that we've done in chemistry has involved electrons, we're not going to worry about electrons here because this is nuclear chemistry or nuclear physics. So this is the summary of the structure of the radon atom in terms of its number of protons, neutrons, and electrons. Now, in our textbook, it gives us an example, so let's just go to our whiteboard here, and the example says an atom has atomic mass number of 234, okay, so the mass number is that A number, the Z number is the atomic number, it has an atomic number of 90, and it says, what element is it, and how many protons, neutrons, and electrons? So if I go to my periodic table and look for element number 90, I see the element thorium. Okay, the element thorium. Okay, thorium is number 90. Okay, but when I look at the mass for thorium, I get 232.04. Well, hang on. I thought thorium was 234. How could it be? Is there a mistake in the periodic table? will actually know, because remember, the numbers on the periodic table are average molecular masses. So let's just look at this one element. The 90 tells me the number of protons, which means it also tells me the number of electrons. And if I want to find the number of neutrons, I'm going to take the mass number and subtract from it the number of protons, and the missing 144 here are the number of neutrons. Right? So I automatically know now how many protons, neutrons, and electrons, and what element it is, just by knowing its atomic mass and its atomic number. Now, let's come back to this idea that the mass on the periodic table is less than the mass of this atom that we're talking about. So, let me go back to my notes. So if I look on the periodic table, so I'm going to finish here. If I look on the periodic table, I see the element lithium, and lithium has a mass of 6.94. You think, how can it be 6.94? It's got to be a whole number, because the number of protons, every proton has a mass of 1, every neutron has a mass of 1. The combination of those should give me a mass which is a whole number, because the electrons basically don't contribute to the mass. So lithium can't be 6.94. I can't have 0.94 of a proton or a neutron. They're whole building blocks, right? They are what they are. They're called nucleons. They're the particles that are inside the nucleus. So of the nucleons that are inside the lithium atom, they can't be a fraction. They have to be a whole number. Now, it turns out that if you go to Bernie Custis and you go into the metals cupboard, you'll find a bottle of lithium. And if I was to take a small chunk out, what I know is that there are 2 kinds of lithium atoms in that bottle. Okay, 2 kinds of lithium atoms. There are lithium atoms that have a mass of 6, and there are lithium atoms in that bottle that have a mass of 7. Now, the ones that have a mass of 6, I know they've got 3 protons because they're both lithium. So it doesn't matter whether the mass is 6 or 7. If I tell you that it's lithium, we automatically know that it is atomic number 3 because it is lithium. But notice the difference between lithium-6 and lithium-7. Remember, the number of neutrons here is equal to the atomic mass minus the atomic number. 6 minus 3 tells me there have to be 3 neutrons in this atom. And this one here on the right, this one has an atomic mass of 7 and only 3 protons, so it's got to have 4 neutrons. So it turns out that what's different about those 2 types of atoms, is the number of neutrons. Some of the atoms are heavier than other atoms in that chunk. Now, if I went to Saltfleet and got their bottle of lithium, it would be the same thing. 80% would be atomic mass 6, 92% would be atomic mass 7. Right? If I went to anywhere on the planet and looked at lithium, it would be 92% lithium-7 and 8% lithium-6. So it turns out that lithium on the planet is always a mixture of these 2 things, 2 different types of lithium. Those are called isotopes. So isotopes are 2 different versions of the same element that have different masses. Okay, one more time. Isotopes are different versions of an element. In other words, they all have the same number of protons, but they have different masses. In other words, they have different numbers of neutrons. Now, that being said, if I was to look at the mass on the periodic table here, it's pretty close to 7. Right? So if I was to, I like to use the example of test marks. If everyone wrote a test, and everyone got 100, except me. Right? And Mr. Sinner wrote the test and he got 50. You all got 100 and I got 50. So 10 people got 100 and 1 person got 50. If I said, what's the class average? Class average would probably be around 95 or 94 or something, 92, whatever it is. Be pretty close to 100, right? Because more people got 100 than got 50. If we wrote the test differently and most of us got 50, but one brilliant person in the class got 100, and everybody else got 50, The class average would be pretty close to 50, right? Because most of the marks would be around 50. Same thing happens in this lithium atom. Because the number of the average is closer to 7 than 6, that's telling me that most of the lithium atoms in that chunk should be 7, and a small number will be 6, bringing down the average. And that's what we see. 92% of them have a mass of 7, and only 8% of them, a small number, have a mass of 6. Right? They're the ones who got 50 on the test. So they're bringing the average down. So the two different versions are called isotopes, and the number on the periodic table is an average mass, or relative atomic mass, but it is the average mass. Right? It's not the mass of an atom, it's the average mass of a bunch of atoms. Okay, so that's what we see on the periodic table. That's why we get some really weird numbers. That's why, let's see here, zirconium is 91.22. Calcium is 40.08. Nickel is 58.69. Right? So when I look at those, now in a lot of cases there can be more than one isotope. There can be many isotopes, maybe a half dozen or more different isotopes on Earth. But most of them will typically be predominantly one isotope will be the most common. And then typically there's a second one, which is the second most common. And between those two, they usually make up about 99% of the atoms in a chunk. So again, if you've got a chunk of carbon, you'd have some carbon-12, you'd have some carbon-14, you'd have carbon-13, right? The different elements would all show up in that chunk. He's saying, well, what if I called the company and I said, I want a bottle of lithium-6? They say, well, I'm sorry, in order to get some lithium-6, you've got to buy a bottle of lithium, and most of that bottle is going to be 7. There'll be some 6 in there, but we can't separate it for you. Right? So isotopes usually come naturally as a mixture of the different isotopes for any element. And even in a compound such as yourself, you would contain in your body some hydrogen 1s, some hydrogen 2s. Right? They would make up most of the hydrogen 1. Right? Remember, the molar mass, the atomic mass on the periodic table for hydrogen is 1.01. What that tells me is that the average mass for hydrogens in your body is hydrogen 1s, with a small number of maybe heavier ones that have got a mass of more than 1. Okay, so there's our first note. I'm going to stop there. So I'm going to leave you with one question on page 663. It's a simple one. You probably could have done it back in grade 9, and you're basically just looking at the number of protons and neutrons given the atomic number and mass and or symbol. So you can work on that, and I'm going to leave you with the OPG assignment, which you can download from the hub, and it should all be there for